among the main mechanisms that characterize TCP protocol is the flow control and the congestion control. Flow control refers to the receiver's ability to basically authorize the sender of how much data it can transmit, because it informs the sender about the current storage capacity of the buffer. On the other side, the congestion control, the sender can adapt the transmission rate according to the current state of the network. Now, let's look at the flow control and how is this done in the TCP protocol. In fact, the receiving TCP can control the flow of the transmitting TCP, because it notifies it what's the state of the buffer, and then it tells the sender whether it should send more data or less data. In fact, from the receiver side, we have a reception buffer, and this reception buffer basically will accumulate the received bytes that have not yet been processed, because maybe application cannot process the information so quickly. So the TCP receive buffer will accumulate a certain amount of segments there. On the other side, on the transmission part, we also have a transmission buffer. And in this case, the transmitter can accumulate a certain number of bytes that wait to be transmitted due to the fact that maybe the network is loaded, and hence the transmitter has tuned down the rate at which it is transmitting information. In fact, a fundamental building block to manage and to define the flow control of TCP is the receive window. Basically, the receive window is defined as the space which is available in the reception buffer to receive new data. Here we see that the receive window is equal to 300 bytes. Again, we should emphasize the fact that when we talk about TCP, everything is referred to in bytes. In fact, the receiving window extends from the last byte that has been delivered to the application to the end of the buffer, in this case from 1100.01 to 1400. Once the receiving buffer receives more segments, in this case the segments which are referred to as a maximum segment size, the receiving window will be adjusted according to the amount of MSS, to the number of bytes that are received in the reception buffer. In fact, here we notice the case in which the reception buffer has received 200 bytes, and hence the receiving window, the one which is remaining, is equal to 100 bytes. At this point, the reception buffer can either wait to fill up so that it receives an additional 100 bytes, or the one that have been received so far are delivered to the application layer. The size of the receiving window is indicated in every segment which is sent from the receiver to the transmitter. In fact, we notice that once the segments have been sent to the application layer, then the state of the reception buffer, in fact the receiving window, is between 1301 and 1600. The TCP error control mechanism is used to, basically as the name suggests, to recover the packets that have been lost in the network. The causes of losing packets might differ, but the main cause of losing the packets in the network can be the overflow of the queues of the equipment, such as routers in the network. The TCP error control, so the way how TCP handles errors, is done through retransmission mechanisms in the same way as the go back N, with the use of the timeout. so without explicit negative acknowledgement. The difference between the TCP and other protocols that we've seen is the fact that it has the capability of accepting segments which are out of sequence. For example, here we see that the receiver has received segment numbered 1, 3, 4, and 5. In this case, what will happen is that the receiver will send to the sender, to the transmitter, an acknowledgement number equal to 2, signaling that the segment which is missing is equal to 2. Only once the segment equal to 2 has been received, will only then the receiver send an acknowledgement number equal to 6, saying that the next byte that I expect to receive is that equal to 6. Now, let's see an illustrative example of how this actually happens. So we consider a packet size in which the MSS, the maximum segment size, is equal to 100 bytes. We consider that the acknowledgement size is equal to 6 bytes, and the window is equal to 4 MSS or 400 bytes. We have the user, we have the server. We can think of these lines as temporal lines. So the sender will send a SN equal to 100 and an acknowledgement number equal to 406. In fact, we notice that while this segment is being transmitted from the user towards the server, the next packet or the next MSS to be sent is identified with the number 200, whereas the acknowledgement number remains as 406. This is true because until the user has received the acknowledgement of the first segment, it will signal the server that the acknowledgement number that is expecting is 406. And this happens also for the case of the third MSS which is sent, which is identified as 300 by the SN and AN equal to 406. Only once the user has received the acknowledgement in which the acknowledgement number is equal to 200 and the sequence number is equal to 406, will then update the sequence number and the acknowledgement number. In fact, we notice that for the sequence number equal to 400 and the acknowledgement number is equal to 412 because it has received the acknowledgement for the sequence number 406. In the same way, we notice that when the sequence number 500 is being sent, the acknowledgement number in this case is equal to 418 because it has received the acknowledgement which has the sequence number as 412 and the acknowledgement number as equal to 300. And this proceeds in the same way as you go in time and as more sequences, as more segments are being transmitted between one entity and the other. But in the real world, what happens is that there are errors. In fact, we notice that for the sequence number 100 and acknowledgement number 406, this segment is correctly transmitted. And the next step is that the sequence number is 200 because we send the new segment, whereas we are still waiting for the acknowledgement of 406. If this packet is not correctly transmitted for some reason, the sender will proceed to send the next packet, the next segment, in this case sequence number 300, while it waits for the acknowledgement number equal to 406. Once the server, in this case, has responded with the sequence number 406 and an acknowledgement number equal to 200, then will the sender upgrade or update the acknowledgement number to 412, to 412. However, notice that since the receiver, in this case the server, has not received the sequence number 200, whenever it replies with the acknowledgement packets, the acknowledgement number is always set to 200. And this is true until the timeout, which has started at the start of the transmission of the second segment, is over. Once the timeout is over, only then will the sender know that the packet that needs to retransmit is the packet with the sequence number equal to 200. This is similar to the example that we showed before, in which the acknowledgement number is kept to 2, even though there have been other segments which have been received, like 3, 4, and 5. And then it proceeds to segment number 6, and in this case, in the same way, the acknowledgement number will be updated to 600 only once the retransmitted segment has been sent from the transmitter side to the receiver side. In fact, one of the problems that pertains to the TCP protocol is also how the timeout is managed, because we notice that when you send a segment, the timeout starts. In case that segment has not been correctly received, then it will be retransmitted only when the timeout has expired. So one of the problems is that we need to determine what is the correct value of the timeout. In fact, if the timeout is too short, it can cause the transmitter to flood the channel with retransmissions because you're not waiting enough. And in case the timeout is too long, then there is the risk of not being able to do fast recovery in case of errors that happened. In any way, the optimal value of the timeout will depend on the network delay. It will depend on the state of the network itself. TCP dynamically calculates an appropriate timeout value by estimating the round-trip time. In fact, the round-trip time itself depends on the network congestion and also on the level of the buffers, which might differ over time, because if a network is more loaded, then the buffers might be more full. Hence, also the value of the round-trip time might be longer, for example. Or in case it's possible to transmit more data, more segments, then the round-trip time can have a smaller value, leading to also the timeout value to be much shorter.